For decades, we've pretty much had one big theory for how AI learns. But what if the brain does something, well, fundamentally different and way more efficient? A groundbreaking new paper in Nature Neuroscience is proposing exactly that. It challenges the very foundations of machine learning and gives us a brand new window into our own minds. Let's get into it. I mean, think about it for a second. You can learn to play the guitar without completely forgetting how to ride a bike, right? But for most AI, learning a new task can literally, catastrophically erase old knowledge. This right here is a huge clue that our brain's learning algorithm might be playing a completely different game. All right, so here's our game plan. First, we're going to define the single biggest challenge for any learning system. Then we'll look at AI's long-standing solution and its major flaw, before diving into the brain's really elegant alternative. We'll see how they stack up against each other, connect this whole theory to how we actually learn, and finally ask what this could all mean for the future of AI. Okay, so at the very heart of all learning, doesn't matter if it's in a human or a machine, is one central problem. It's called the credit assignment problem. Imagine your brain is this giant company with billions of employees. Those are your neurons. Now, if the company messes up, how on earth do you figure out which specific employees out of all those billions are the ones who need to change what they're doing? That, in a nutshell, is the absolutely massive challenge of credit assignment. For the last 40 years or so, AI has had this incredibly powerful, almost magical answer to this problem. It's called backpropagation, and it is the engine behind pretty much everything, from ChatGPT to self-driving cars. But, as we're about to see, this reigning champion has a really critical flaw. And look, this wasn't just some niche theory. For decades, the entire field basically assumed that backpropagation was the best solution. So much so that a lot of people just figured the brain must be doing something very, very similar. To really wrap our heads around this flaw, the paper uses a brilliant analogy. So let's imagine a bear, and it's just standing by a river. So the bear sees the river, and it correctly predicts two things. It's going to smell salmon, and it's going to hear water. But today, maybe the wind is blowing the wrong way, so it only smells the salmon. It doesn't hear the water, so there's a prediction error for the sound. Now, backpropagation fixes this by tracing that error backward and weakening the connections coming from the site of the river. Here's the problem. This weakens all the predictions. So next time, yeah, it'll correctly expect to hear less water, but it will also incorrectly expect to smell less salmon, even though that prediction was perfect. That right there is catastrophic interference. So, if the brain isn't doing that, what is it doing? Well, this paper proposes a totally different idea. It's called perspective configuration. You know, the easiest way to get this is to stop thinking about the brain as a computer and start picturing it as a physical machine, like a bunch of nodes connected by springs. Instead of just tweaking one faulty spring after something goes wrong, learning is about the entire machine settling into a brand new, stable, low-energy configuration that accounts for all the new information at once. And right here, this is the absolute most important difference. It's kind of mind-blowing. Backpropagation learns reactively. It sees an error, then it changes its connections, and its behavior changes as a result. Prospective configuration learns proactively. It flips the last two steps. First, the network figures out the ideal pattern of activity, like the perfect state of mind that would have gotten the right answer. It's only after it finds this ideal future state that it updates its connections to make that new way of thinking permanent. Okay, so that sounds really elegant in theory, right? But does it actually work any better? Well, the researchers put it to the test. This chart shows the difference in efficiency just perfectly. Think of target alignment like pointing an arrow at a target. Is every little adjustment you make actually getting you closer to the bullseye? In really complex networks like our brains, backpropagation's adjustments can kind of conflict with each other, and they end up pushing the arrow off course. But perspective configuration, it keeps the whole learning process aimed squarely at the solution, which makes it way, way more efficient. And this efficiency, it's not just a theory, it translates into huge advantages that look a lot like how we learn. This new model is better at learning from just a single experience instead of needing thousands. It can learn new stuff without wiping out the old stuff. It adapts to change, it learns from very little data. All of these are the hallmarks of real biological intelligence. But honestly, here's the most compelling part. This new model doesn't just crush it in simulations. It can actually explain some really puzzling results from real experiments with human beings. So in one experiment, they had people learn to move a joystick that had this hidden force pushing against it. A blue background meant the force would push one way, and a red background meant it would push the other. Pretty simple. But then, of course, the researchers threw a curveball. What happens if a person sees a red background, but they feel the force that was supposed to go with the blue background? How would they even learn from that? And the results are just fascinating. A backpropagation model predicts you'd learn nothing about the blue context because, well, you never saw the blue color. But that's not what people do, is it? We're smart. We can figure out, hey, wait a second, I felt the blue force, so this feedback must be about the blue context, even though I'm seeing red. And what's remarkable is that the perspective configuration model predicts this very sophisticated human behavior perfectly. So, where does this leave us? What does all this mean? We could be looking at a really revolutionary shift in how we understand learning, both in ourselves and in the machines we build. If you remember one thing, let it be this. The brain isn't just passively correcting errors after the fact, it's an active prediction machine. It first figures out the ideal state of mind, the right way to think that would have led to the correct outcome. And only then does it use plasticity, physically changing its connections, to hardwire that better way of thinking into its own structure. This just completely reframes how we think about learning. It suggests a path toward AI that's more stable, way more data efficient, and much more adaptable. An AI that doesn't just mimic intelligence, but actually learns with the same clever principles that nature's been refining for millions of years. The only question now is, what are we going to build with it?